Welcome, fellow mathletes. It's time for 3.2. Oh, yeah. All right, here we go. Let me share my screen. And we're going to talk about linear functions. Okay, so remember in 3.1, we talked about what a relation is, and then we have certain relations that are a function. And now we're going to talk about a certain type of function or certain types. And one of those types is what we call a linear function, okay? So your learning target for today is to determine whether a function is linear or nonlinear. And linear, what does that mean? Think of linear. It's whether the inputs and outputs for the function line up, okay? Nonlinear would be something that's not in a line, okay? All right, so obviously you can work with your imaginary partner, or if you're doing this with somebody, maybe you're doing that, or you can do it with someone at home, or you can just do it by yourself. So you're gonna copy and complete each table for the sequence, okay? And in parts A and B, use the rectangle shown here, okay? So graph the data in each table, okay? Decide whether each pattern is linear or nonlinear, okay? So what we're going to do is we're basically giving you various inputs for X, okay? And then you have to figure out the perimeter of the rectangle, okay? So here's the deal. Let's go through this. I'll do the first one together. So let's pretend X is 1. Okay, well, remember what the perimeter of a rectangle. It's twice the length plus twice the width. So what would the width be if X is 1? It would be 1, right? And the length would be 2 times 1, or 2. So we'd have 1, 2, and then another 1 and another 2. So the perimeter would be what? 6. Good, because 2 plus 2 plus 1 plus 1 is 6 last time I checked. Okay, now try it if X was 2, and then 3, and 4, and 5. Okay, so go ahead and pause and try that. Hopefully you got 12, 18, 24, and 30. Okay, now what we're going to do is we're going to go and graph this data. Okay, so you're going to go to X is 1, P, which is Y, right? See how it's the y-axis is labeled P for perimeter, and we're going to label these. So go ahead and label those points: 1, 6, 2, 12, 3, 18, 4, 24, and 5, 30. Go ahead, pause the video. Okay, I'm back. So what's that going to look like? It's going to look like that. See how with those points? So do you think it's a linear function or not? Yeah, they line up. It's linear. Okay, awesome. Okay, let's try another one. Now we're going to do areas. Remember what the formula for the area of a rectangle is. What is it? Hopefully you said length times width. Okay, so here we go. If X is 1, this would end up being a width of 1 and a length of 2. 1 times 2 is 2. Okay, now fill in the rest of them. So hopefully you got 8, 18, 32, and 50. Okay, and then pause the video after you and go plot those points on your graph, and let's see if they form a line or not. Okay, hopefully you realize that it's not a line. Okay, it's not. So would it be linear or nonlinear function? Nonlinear. Okay, now I want you to notice something else. Let's go back here. Do you notice how every time X increases by 1, P increases by 12? 1 to 2, that's a jump of 1. 6 to 12, that's a jump of 6. 2 to 3 is a jump of 1. 12 to 18, jump of 6, and so on and so forth. Okay, notice here, and that one was linear, right? We got a nice line, right? Okay, but notice here, as X increases by 1, the area increases by 6, and then 10, and then a lot more than 10, and then a lot more than that, and so forth. Okay, so just something to notice at this point. Okay, so how are we going to identify linear functions? Well, we kind of just gave you some clues on that. But a linear function in 2 variables, x and y, so let's pretend we're using x and y for our inputs and our outputs, is an equation that can be written in the form of y equals mx plus b. So if you can put an equation into that form where we'd have a number plugged in for m and we'd have a number there for b. So it could be y equals, 4/5 x minus 12 or something like that, okay, where m and b are constants. So we would have numbers plugged in for that. The graph of a linear equation is a line, okay? Likewise, a linear function is a function whose graph is a non-vertical line. Why non-vertical? Think about what we've learned about functions and determining whether something is a function or not. Well, one of those ways was that vertical line test, right? So if a line's vertical, it would fail the vertical line test, right? So it's any non-vertical line. So it could be like this, it could be horizontal, it could be like that, it could be any of these, but not that one, not a vertical line, okay. A linear function has a constant rate of change, and we saw that right back here, we saw that. Up 1, up 6, up 1, up 6, okay? We saw a constant rate of change. And it can be represented by a linear equation in two variables. Y equals mx plus b would be the form you could write it in. A nonlinear function doesn't have a constant rate of change. So its graph is not a line, like this one, right? Wasn't a constant rate of change. All right. So just looking at this and looking at this table, okay? Do you think this is a linear function? No, of course not. Does that look like a line? Absolutely not. Notice the increases here. 3, 3, 3. Oh, this is a different one. I'm sorry. This is different than this. But does this one? No, it's not a linear function. Okay. What about this one? Yeah, it looks like a line to me. Okay. All right. What about this? 1 to 3. So these are all going up by 2. Are these all going up by the same amount each time? Oh no, 7, 11, 15. So that would not be a constant rate of change. So this is nonlinear, linear, nonlinear, linear. Okay, so try these on your own. Okay, I'm back now. So is this one a linear function? You betcha. What about this one? No, the graph's not a line. Okay, what about these tables? Do these represent linear or nonlinear? Hopefully you got linear. As x increases by 1, 1, 1, 1, 2, 2, 2. It's a constant rate of change. What do you think about this one? Up by 1, down by 8, down by 4, down by 2. That's not constant. That's a nonlinear. Okay. All right. Great. So, okay, remember, it just has to be in the form of y equals mx plus b. Can you put y equals 3.8 into that form? You might be saying no, but the answer is actually yes, right? Because couldn't you make mx like 0x? So couldn't you write this as y equals 0x plus 3.8? So that would be a linear function. And you'll see what kind that is. This would actually end up being a horizontal line. Okay, what about y equals the square root of x? No, we don't want square root of x. We want an x, right? You might be saying, well, what if I squared both sides? Well, then you would have an x, but you'd have y squared, and that's not the form. It's y equals mx plus b. So the answer is no. This one, an exponent with a variable? No, come on, give me a break. What about this one? No, that wouldn't work either, because that's x to the kind of the -1 power. We'll get into that later, but no. What about this one? Yeah, you could distribute, then it would be y equals 6x minus 6. So yeah, this one, x squared? No, that's not what we're talking about. We're talking y equals mx plus b. Okay. Yeah, and so here's a good explanation. So you can go ahead and read that. You cannot rewrite those in the form of y equals mx plus b. So they cannot represent linear functions. But the other ones you can, right? Again, here's y equals 0x plus 3.8. And you can distribute here and get y equals 6x minus 6. Okay. Okay, what about these? You try these on your own. Pause the video, try them on your own. Okay, hopefully you said this one is linear, right? You could always write 1x plus 9, not that we ever do, but we know that the one's there. What about this one? Yeah, we could write this as 3/5 x, and then we could always put a plus 0 in the end. Is it in the form of y equals mx plus b? Yeah, it sure is. What about this one? X squared? Nah. By the way, if you go and graph this, you'll see it's actually going to be in the form of a parabola. All right, on we go. So just a quick review, remember, with functions, each input can only have one output, okay? Can two inputs have the same output? Yes, but each input can only have one, right? So we can see those in the forms of an input-output table, a mapping diagram, words, an equation, and now we're seeing that we can do that in a graph too, okay? All right, if you had enough and you want to take a break, this would be a good time to take a break. So you can pause the video, go do something else and come back, but we'll go ahead and continue on now here on the video. Okay, so a solution of a linear equation in two variables is an ordered pair, x comma y, that makes the equation true. So just like before when we had x plus 3 equals 5, and we said, okay, well, what value of x will make the equation true? Same thing when you have two variables, you're just looking for an x and a y that make it true. And there can be a bunch of them, right? Because a line is consisted of a bunch of points, okay? So real important here, in green, it says the graph of a linear equation in two variables is the set of points, x comma y in that form, right? In a coordinate plane that represents all solutions of the equation. So when you graph a line, that's graphing all the solutions of that particular equation, okay? There's an infinite number of pairs that make up the line, okay? All right, so we have two, remember domain and range, remember that for functions? So domain is the inputs, right? So we have two different types of domains for functions. One is what we call a discrete domain, okay? And that means that the set of input values, your inputs, is only certain numbers in an interval, okay? So it's only 1, 2, 3, 4, and 5, okay? It's the integers from 1 to 5. It's not 1.7, it's not 2.5, it's just 1, 2, 3, 4, 5. See how just those points are graphed there? Okay. You can contrast that with what we call a continuous domain, okay? And that's where the input values, or the inputs, consists of all real numbers in an interval, okay? So it's not just 1, 2, 3, 4, 5, but it's 1.00001, 1.1, 1.2, 1.3, there's an infinite number of numbers in that area. We call it continuous, okay? So those are our two types of domains: discrete domains, continuous domains. Okay. So looking here at this chart, here are your inputs, here are your outputs: number of stories, height of a building. Okay. Is this domain discrete or continuous? Well, it's listed out here: 1, 2, and 3. Which one does it look like? Yeah, it looks like just this one, right? Think about it this way: can a building have a half a story? No, it might have a shorter story or one with a smaller roof or a smaller height, but you don't have half a story in a building, right? So that answers that one. Yeah, it would be discrete, right? The number of stories must be a whole number. Come on. All right, good. Now look at these. Is each domain discrete or continuous? Go ahead and try them on your own and see how you do. Okay, well, hopefully for this one, you got that it was discrete. This one would be continuous, right? Because it's not just those certain points, it's every single real number that is on that number line. And there's even though it's just a line segment, it's not a line, there's an infinite number of ordered pairs that you could pull on that. There's an infinite number of points that make up that line. Okay, how about this one down here? Right, discrete, right? It's just those, what is that, 7 points, right? But here, it's an infinite number of points here in there. So it's continuous. Okay. All right. So let's try this in the form of some word problems here. Oh, we can do this. Deep breath. Go to your happy place. Yes. All right. Okay. The linear function y equals 15.95x represents the cost y in dollars of x tickets for museum. Each customer can buy a maximum of 4, ooh, and that's highlighted, that must be important, tickets, okay? Remember, feel free to mark up your your paper here, like circle important things, star them. You can use highlighters, anything you want. Okay, so let me make sure I understand this. So, okay, y is the cost of that you're spending, and that's represented by $15.95 for each ticket you buy. Okay, so the cost of the ticket per ticket is $15.95. Your total cost is what y is. Okay, A, find the domain of the function. Is the domain discrete or continuous? And then explain. I'll give you a hint. Can you buy part of a ticket? No. So what does that mean it is? It's discrete, right? And the domain itself is what? 0. If you decide not to buy a ticket, you think $15.95 is a ripoff for the museum, right? Or you might buy 1, 2, 3, or 4. But can you buy 5? No, you can't. And you can't buy part of a ticket. Okay, and now we're going to graph the function using the domain. Okay, so in other words, notice your labels here, number of tickets and the cost. So if you buy 0 tickets, what's the cost? Yeah, $0, right? So they made this table. Okay, so you can see here, their input is 0. If they input it into 15.96, 15.95, excuse me, 15.95 times 0, what's spit out? 0. So our ordered pair would be 0, 0. So we'd have a point right there. Well, what would it be if we bought 1 ticket? It'd be $15.95. So we have a point that's at 1, $15.95, right? And you can fill in the rest. And what are you going to see? What should the graph look like? What do you think is going to happen with the points? Yeah, they're going to line up. For every ticket you buy, for every time you increase the input by 1, how much is the output increasing by? 15.95. So it's going to be linear. Okay, cool. All right, so here we go. Cereal bar contains 130 calories, okay? I don't eat a whole lot of cereal bars, but I eat a lot of protein bars. I don't know if you guys know this, but I'm vegan, so I have to find good sources of protein, and there's these great protein bars that kind of do the trick for me. Love them. They're really tasty too. Anyway, that's a sidebar. Sidebar, get it? Cereal bar. Oh, God, that was good. A cereal bar contains 130 calories. The number C of calories consumed is a function of the number B of bars eaten. Okay, yeah, that makes sense. So, yeah, because the more bars I eat, the more calories I'm consuming. In fact, for every bar, I'm consuming how many calories? Yeah, 130. Okay. So what do you think? Do you think this situation represents a linear function? I hope you said yeah, right? Because as the number of bars you eat increases by 1, the number of calories you consume increases always by the same number, 130, right? Okay. Think about it. If you ate 1 bar, it'd be 130 calories. If you ate 2 bars, it would be 260, right? It's going up by 130 each time. So it's a linear function. It's good though. It's going to line up. Okay. Do you think the domain, we'll find the domain. Is there any limit here on how many bars you can eat? Not that I'm aware of. Well, I mean, eventually your stomach will explode or you'll just get so sick. Is the domain discrete or continuous? Can you eat part of a bar? Can you have just a nibble? Can you have 1.5 bars? So yeah, you can eat part of a cereal bar. So the number of bars eaten can be any value greater than or equal to 0. It can't be negative, right? You can't have a negative bar. Well, I guess you could in one situation, but that'd be disgusting. We're not going to go there. So the domain is B, the number of bars is greater than or equal to 0. I hope you see how that takes into account like having 1/3 of a bar or 1/4 of a bar, anything greater than or equal to 0. And that would be what? That would be continuous, okay? So how would you graph something like that? Well, you might start by graphing some points, but remember, it goes on forever, right? Someone might be eating, 100 bars. That would be gross, but they could, right? So what do you're not going to have to graph all those points. So what do you think you're going to do? Well, you might start plotting them, right? But then eventually you're just going to want to put an arrow on the end to show that it continues at that linear rate, right? The same rate every time the number of bars goes up by 1, the number of calories goes up by 130 forever, okay? theoretically. Okay, not everyone's gonna eat that many bars. Okay, good. Hopefully you're getting this. Okay. All right. So the linear function m equals 50 minus 90 represents the amount m in dollars of money you have after buying DVDs. Okay, so let me think about this for a sec. So if I spend money on DVDs, the amount of money I have, like in my wallet or whatever, goes down, right? Because I'm shelling money out of my wallet. So it's going to go down. And it's going to go down by how much per DVD? Oh, 9. So 9 what represents what? The cost of a DVD. What does the 50 represent? Hopefully you said the money you started with, because think about it. If you bought 0 DVDs, wouldn't M end up equaling 50 minus 9 times 0, which is 0, so equals 50? Okay, so let's look at A, now that we understand. Notice how I'm going through these questions. I'm really like analyzing everything that's said there and making sure I really understand the question before I move on. That's what you should be doing. Okay, A, find the domain of the function. Is the domain discrete or continuous? Okay, how are we gonna do this? Well, is it discrete or continuous? Hello, Mr. DVD seller down at the music store. I'd like to buy, or the video store, not that they have those, Mr. Redbox in person. I'd like to buy half a DVD. No, I don't think so. So you can only buy them. So what do you think? So is it gonna be discrete or domain or continuous? Discrete, right? Either by 1 or 2 or 3 or 0, right? 0, 1, 2, 3, but then you only have 50 bucks to spend. How many can you buy? Well, you can't spend over 50 bucks, right? So think about it. What would that be? Well, 9 times 5 is 45. So I could afford buying 5 of them. Could I afford 6? No, because remember, negative 9 times 6 would be what? Negative 54. 50 and negative 54 would mean I'm spending money I don't have. I only have 50 bucks. So hopefully you got the domain was 0, 1, 2, 3, 4, 5. And it's discrete because you can't buy part of a DVD. Okay, and then what would it look like if you went to graph this? So let me ask you this. Again, if you didn't buy a DVD, how much money would you have left? 50, right? Ooh, see why we have that point up there, right there at the top? 0, 50, I'll put it right there. Okay, what would be the next one? If you bought 1 DVD, how much money would you have left? Hopefully you said, oh, it would be 50 minus 9, which is 41. So we would go and we would graph 1, 41. What if you bought 2? It's going to be down there, and you could probably predict where the rest of them go, or you could actually just go ahead and do it, right? You'd have all that. Okay. By the way, remember, you don't have to, if you've labeled your axes in any way, you don't have to label the points. They're kind of doing a little bit of overkill. I get these from the textbook. Okay. All right, one more. So a 20-gallon bathtub is draining at a rate of 2.5 gallons per minute. The number of gallons the number G of gallons remaining is a function of the number M of minutes. So what's going on here? You took a bath. And what do you do after you finish taking a bath? Yeah, you pull the drain thing out, plug out or whatever, or you hit the knob thing and it starts draining out. And it goes at a constant rate, or at least it appears to be, right? It seems like it would be, yeah. Okay, so do you think this situation represents a linear function? Yeah, seems like it would drain out as much as the pipe can take, right? So yeah. And it says it's 2.5 gallons per minute. It's not saying it's increasing or decreasing. So yeah, it's constant. So as every minute goes by, the number of gallons left in the bathtub goes down by 2.5. That's a constant rate of change. Okay, find the domain of the function. Is the domain discrete or continuous? Okay, so does it drain for 1 minute and then skip right to 2 minutes? No, of course not. You can drain for seconds or milliseconds or whatever. So would it be discrete or continuous? Continuous, good. All right. Now, the domain here is going to be what? It's the number of minutes. So you'd have to figure out, how many minutes would it take to drain 20 at a rate of 2.5? See if you can figure that out. Okay, hopefully you realize that it would be at most 8 minutes. 8 times 2.5 is equal to 20, okay? And then if you go and graph it, okay, in the bathtub, you right when you pull it out, how much is left, right? You haven't started, you're at 0 minutes, you're going to be up at 20, right? Oops, don't want to move that, I want to move this. Okay, then you're going to want to plot another point. So let's say you go and you plot after 2 minutes. Really, you could pick anything you wanted, but if you picked after 2, right, what's 2 times 2.5? 5. What's 20 minus 5? 15. And then let me ask you this, do you really need to plot any more points than that? Not really. Why don't we put an arrow though down here? Can you have a negative number of gallons in the bathtub? No, when it drains, it's down to 0. So this would stay here in the first quadrant and finish right here. All right, well, that does it for 3.2. Covered a lot there. There's some good terminology. Make sure you understand it. You know them, maybe flashcards, something along those lines. Come see me, happy to help. This is fun because this is really getting into more real life stuff. So anyway, hope you enjoyed it, and good luck. And remember, take good advantage of contact time. I really want to make sure that you use that, and I'm happy to help. In fact, I look forward to it. All right, see you later.